Welcome to the second lecture of Module 5. In this lecture, we're going to be deriving some Pauli spin matrix identities. They're quite remarkable relations that you're going to get out of this. And we're also going to do very similar identities for a set of matrices that are called symplectic matrices. I know that you've probably never heard of symplectic matrices before, but you're going to find that they are interesting matrices, and we actually need them when we work on what are called squeezed states when we talk about photons toward the end of the class. And so it's very important that we work out this identity here as well, and it's going to come in very handy and be very important later in the class. All right, so we're going to start by looking at the products of Pauli spin matrices. We have to recall the identity that we worked very hard to derive last lecture, which involved the product of two Pauli spin matrices. Sigma I times sigma j is equal to delta ij times the identity matrix plus I, the sum over k, epsilon ij k times sigma k. I want you to really be clear that the right-hand side and the left-hand side are both 2 by 2 matrices. And so this is an equality between different 2 by 2 matrices. We're going to use this identity to derive an identity for the product of an inner product of a real vector with a Pauli spin matrix vector. So we're going to look at A dot sigma. A is a vector, so it's an AX, AY, AZ with AX, AY, AZ all numbers, and sigma is the Pauli spin matrix vector. So that inner product is AX sigma x plus AY sigma y plus AZ sigma z. And we're going to look at the product of two different inner products of vectors with Pauli spin matrix vectors. And we're going to derive an identity for that. So the first thing I want to do is I want you to recall the way that we write an inner product. It's typically written as a sum over I, AI sigma I. And as I mentioned before, that becomes AX sigma x plus AY sigma y plus AZ sigma z. And we can write it in this abstract form as a sum over I, AI sigma I. I'm working very slowly and carefully here because I find students often struggle when we work with these summations and we manipulate them. So I just want you all to be well grounded that that is the way that we get an inner product. Okay, so we have two of these inner products. So we're going to use I for the index in the first sum and J for the index in the second sum. And so we get sum over I, AI sigma I, sum over J, BJ sigma J. But now we can move those two summation signs all the way to the left, and we can move the AI and the BJ all the way to the left, and we're left with this product, sigma I, sigma j. Well, that's just waiting to use our identity for the product of two Pauli matrices. So let's go ahead and substitute that in. And you see we have this delta ij times the identity matrix plus I sum over k epsilon ij k sigma k. You can see I didn't write the identity matrix in there. Sometimes I leave that out. It's usually easily understood when the identity matrix is present. But I will try to keep it in for most of the formulas in this lecture. All right, the delta ij, if you recall, delta ij is equal to 0 unless I equals j. So I can get rid of the j sum because the j must equal I, otherwise I have a 0. And that means I'm left with a sum over I of AI bi. That's the inner product of the A vector with the B vector. Similarly, with the second term, I can move that sum over k. I can factor the I out. And you can see I'm going to have a sum over ijk AI bj sigma k times this epsilon ijk. Well, if you go back and remember from your vector calculus class, that's the vector triple product. It's going to be A cross B dot sigma vector. And so let's see that explicitly in equations. You get A dot sigma multiplied by B dot sigma is A dot B times I plus A cross B dot sigma. And I want you to be sure that you remember that this is a matrix equation. There are matrices on both sides of this equation. The vectors in them are actually just producing numbers that are multiplying the different matrices and are creating linear combinations that we're adding together. We're going to see just how complex this is in just a moment. All right, this is actually a very powerful identity, and it's a very compact way of writing some rather long expressions. I'm going to focus on two particular properties, both which I find somewhat unusual. The first thing we're going to look at is the case where A is equal to B. There's a very similar formula where A is parallel to B, but for the moment we're going to consider the case where A is actually equal to B. That's the one that we're really going to need. So if A is equal to B, then the second term is equal to 0 because A cross A is equal to 0. and I'm just left with the first term, and I get A dot sigma quantity squared is equal to the modulus of A squared multiplied by I, the identity matrix. What this says is this following remarkable result. I'm writing down for you A dot sigma. That's AX sigma X plus AY sigma Y plus AZ sigma Z. It gives that complicated looking mess. However, when I square that matrix, I'm going to get the modulus of A squared times the identity matrix. I know it's hard to believe that that is actually what you get, but it is. And indeed, if you do not believe me, I encourage you to pause this video and just check it directly by doing the matrix multiplication. All right, let's look at the second property. The second property occurs when A is not parallel to B. Then the second term is non-zero. And we get what is just a ridiculously complicated matrix. I mean, just look at that. It's horrid. Okay, you'd never want to have to write that down. But it doesn't look so bad when we write it in our compact form. It's remarkable that that product is really so complex, and it's coming about because of that second term, which involving the triple product really has a lot of terms, and it's very complicated. All right. We're going to now look at one of our main identities that we're trying to derive, the exponential of the Pauli spin matrices. Now, you've actually covered this already in Physics 155, so this should be a fairly quick review, but I also know that even though you covered it in Physics 155, you're not going to be experts on it. But if you want to see it again, in addition to what you've seen here, you can go back to Physics 155 and take a look at what we did it there. It was an in-class problem that we worked through. So what we learned was that the exponential matrix satisfies this identity. E to the I v dot sigma, that's a vector of numbers v dotted into the Pauli spin matrix vector sigma. The way that we evaluate the exponential is via the power series. It's equal to the sum n equals 0 to infinity of I v dot sigma raised to the nth power divided by n factorial. Okay, that looks hard to evaluate. We've got to evaluate these powers of these matrices. Okay. But here's where we bring in the identity that we just derived. We just showed that I v dot sigma squared is equal to minus the square of the norm of v multiplied by the identity matrix. The minus sign is coming from the I squared. So that means that in the summation for the exponential, I should divide my terms up into the even powers and the odd powers, and then use my identity for both of those cases where I've separated out the sum. So here you go. Here are the even powers. The even powers are giving me this term sum m equals 0 to infinity minus norm of v squared raised to the nth power divided by 2m factorial multiplied by the identity matrix. I'm going to rearrange that. I'm going to just tell you how you do that. Pull out the minus 1 to the m. Rewrite that v squared to the mth power as modulus of v raised to the 2m power, and it's divided by 2m factorial. I hope you can recognize that as the power series for the cosine of modulus of v, multiplying I. The second case, the second summation, I can pull out a minus 1 to the m. I have this v squared raised to the mth power. Again, I can write that as modulus of v raised to the 2m power. It's divided by 2m plus 1 factorial. It looks almost like the power series for the sine, but I'm missing a power of v. So I'm going to use my multiply by 1 trick to multiply by a mod of v and divide by a mod of v, and I will get minus 1 to the m v mod of v to the 2m plus 1 divided by 2m plus 1 factorial multiplied by the matrix I v dot sigma divided by mod v. And now that summation is the sine of mod v. So now we can summarize that and put that together. We get this identity. It looks almost like the Euler identity. E to the I v dot sigma is cosine v times the identity matrix plus I sine v multiplied by v dot sigma divided by mod v. That v dot sigma divided by mod v is kind of like a unit 2 by 2 matrix because I'm dividing v dot sigma by its length, which we just worked out because v dot sigma squared is equal to mod v squared, and the square root of that is mod v. So that's kind of like we're dividing it by its length. All right, so we've just showed you that this exponential has this Euler-like relation. The identity that we derived here is extremely powerful, and we're going to be exploiting it in class next. We're going to use it to derive what is called the exponential disentangling identity. The exponential disentangling identity is a very powerful identity. It's our second of our fundamental operator identities that we'll be using in this class, and we're going to find that we can do a number of very remarkable things with it. So it's a very important result that we'll be deriving in class using what we have just derived here in this lecture. Okay, it's time to move on to these symplectic matrices. I know you've never heard of them before. Please don't be afraid just because the name sounds really weird. They're very easy, concrete, down to earth. This lecture is something you should be able to follow. So, with spin, we had these commutation relations, which are now being expressed in terms of the Pauli spin matrices. The commutator of sigma z with sigma plus minus is equal to plus minus sigma plus minus, and the commutator of sigma plus with sigma minus is equal to 2 sigma z. Those commutation relations you should think of in terms of matrices. Sigma z commutator sigma plus minus is sigma z times sigma plus minus sigma plus minus times sigma z. You just look at the difference of those two products in opposite order of the matrices. Since we know the matrices, it's very easy to do these calculations. All right, the symplectic matrices are a set of 2 by 2 matrices that satisfy the following commutation relations. K0 with K plus minus is equal to plus or minus K plus minus. Looks very similar to the Pauli spin matrices. And then K plus with K minus is equal to minus 2K0. It's that minus sign that is the only difference in this algebra. But it turns out that rather innocuous looking minus sign actually leads to quite different matrices that we will be using to represent that algebra. And I've written them out for you here. Now, they look a bit like the Pauli spin matrices, but there are some sign differences. It's conventional to divide by a factor of 2, so all of these are a factor of 2 smaller than the similar Pauli matrices. And, you know, this is what they are, but I don't want you just to take my word for it. We really need to go ahead and plug in those matrices into these commutation relations and verify that they work. So let's go ahead and check. So this is just to remind you what we're going to be working on and what those matrices are. Our first check is the commutator of K plus with K minus, which is supposed to equal minus 2K0. So you see I've copied a K plus on the left and a K minus on the right in that first factor, and then I have a K minus on the left and a K plus on the right in the second factor, and there's a minus sign between them. Now we have to do the matrix multiplication. On the term on the left, I have a 0, 0, where that's going to give me a 0, 0 in the matrix multiplication in the top row. Then I have a minus 1, 0. When that multiplies the first column, it's a 0, 0, so I get 0. When it multiplies the second column, I get a minus 1. So this is a matrix that will have zeros everywhere except a minus 1 in the lower right corner. Let's look at the second one. When I multiply 0, 1 times the 0 minus 1, I'm going to get minus 1, but there's a minus sign in front of that, so I'm going to get a plus 1. And that's going to be in the upper left corner of the 2 by 2 matrix. And you can verify that all of the other matrix elements are 0 by doing the matrix multiplication. Now, when we add those two together, we get 1, 0, 0 minus 1. Let's look at K0. Indeed, you can see that is minus 2K0. So we have verified the first commutator identity. Let's look at the second. This is K0 with K plus. So we're going to write out the K0 on the left and the K plus on the right in our first factor, and the K plus on the left and the K0 on the right in our second factor. Now let's take a look at the first factor. Minus 1, 0 times 0 minus 1, that's 0. Minus 1, 0 times 0, 0, that's 0. 0, 1 times 0 minus 1, well, that's minus 1, and there's a half in front. So I get a minus 1 half in the lower left corner of the matrix, and then 0, 1 times 0, 0, that's 0. So there's only one non-zero matrix element. Let's look at the second product. 0, 0, that's going to give me zeros in the upper row. Minus 1, 0, that's going to hit the minus 1, 0 in the first column, so that lower left matrix element is equal to a half, but there's a minus sign in front of it. That adds with the minus 1 half that we already have and gives me a minus 1. And then the last element, minus 1, 0 times 0, 1 gives 0. And so I'm left with this matrix that's 0, 0, minus 1, 0. And indeed, that is equal to K plus. Now, we just need to check the last one. K0 with K minus is minus K minus. I'm not going to talk you through this. I encourage you to pause the video and just work it out for yourself. It's a couple of matrix multiplications and adding together. And you find again that you're going to get here 0, 0, minus 1, 0, and that's minus K minus. One thing I want to point out, because it's going to come up very important on the next slide, if I instead evaluated the anti-commutator between k0 and k plus, I will change those minus signs to plus signs, and then these last two are going to cancel and give 0. So the anti-commutator of k0 with k plus and the anti-commutator of k0 with k minus are both equal to 0, and that's going to be very important on the next page. All right, we're going to work out this exponential identity for the symplectic matrices. We're not working with Cartesian symplectic matrices. People just tend not to do that very much. They instead work with this k plus, k minus, and k0. And it's not going to be e to the I times some linear combination. We're actually working with e to the minus c k plus 2I eta k0 plus c star k minus. C is a complex number. Eta is a real number. And I know that looks like it comes completely out of the blue, but it turns out that's the important exponent that we want to take when we're working with symplectic matrices. And that's the one that's going to be very important for us to work with later in the class. So you just have to trust me that that's the right thing to work with. Okay, let's calculate it. The way that we're going to do this, again, we're going to expand this in a power series, and we're going to need to calculate powers of the exponent. And so let's look at squaring the exponent. So we just do the FOIL method. I'm going to first summarize the squared matrices. So I get c squared k plus squared minus 4 eta squared k0 squared, the minus coming from the I squared, plus c star squared k minus squared. Those are all the squared terms. Then I have the cross terms. But now you have to be very careful. Order matters, so I have to write down both forms of the cross terms, and they're going to give me anti-commutators. I'm going to get 2 minus 2I c eta k plus k0 plus k0 k plus 2I c star eta k minus k0 plus k0 k minus c squared k plus k minus k plus. All right, we have to evaluate these things. Remember, k plus and k minus are nilpotent matrices. When we square them, we get 0. Just like the raising and lowering operators for the Paulis. When we square those, we got 0 as well. K0 squared, that's like a Pauli sigma z. It squares to something proportional to the identity. Here it's 1/4 of the identity. As I discussed on the last page, the anti-commutator of k0 with k plus and the anti-commutator of k0 with k minus are both 0. You have to actually go out and work through what the anti-commutator of k plus with k minus is. It's not that hard. You can do it using the material from the previous page, and you'll find it's equal to minus I. And so when we now take those results and plug it into what we FOILed out above in that equation, you find only 2 terms survive, and they give us c squared minus eta squared times the identity matrix. So we have the very same kind of identity as we had with the Paulis. We're going to be working in cases where c squared is bigger than eta squared, so that number is always going to be a positive number. All right, so this is going to allow us to compute the exponential because we have this very nice simple identity when we square the exponent that we're calculating the exponential of. All right, let's remind ourselves how to do that. We write the exponential out as the power series. Because of this squaring identity, we're going to separate out into the even and the odd powers. The even powers are going to look like c squared minus eta squared raised to the mth power divided by 2m factorial multiplied by the identity matrix. I'm going to write that as the square root of c squared minus eta squared raised to the 2m power. And now that would be the cosine power series if it had a minus 1 to the m, but it doesn't. And that actually means it's a hyperbolic cosine power series. If you don't recognize that, or you're unfamiliar, or you've forgotten what hyperbolic cosines are, I do encourage you to do a brief refresher on what a hyperbolic cosine is from Khan Academy or from what we learned in Physics 155. And so we're going to get a hyperbolic cosine of the square root of c squared minus eta squared times that identity matrix. The second power series almost looks like a hyperbolic sine power series, but again, we're missing a power of the square root of c squared minus eta squared. So we're going to borrow that by doing a multiply by 1 trick. We're going to multiply by the square root and divide by the square root. That will then give us a hyperbolic sine of the square root multiplied by the matrix given by that quantity in the parentheses divided by the square root of c squared minus eta squared. And there it is. That's what you get. It's kind of a messy identity, But it's a really nice simple identity, and that's the identity that we're going to be working with. In the class that we're working together on this project with, what we're going to be doing is we're going to be taking these identities and using them to work out what are called the exponential disentangling identity, which is a really powerful identity. And as I mentioned before, that's fundamental operator identity number 2 for the course. We have a total of 4. So we're going to be hitting the second one in class together with the material that we're going to be working on. And that concludes lecture 2 of module 5.